I can certainly treat your body as a quantum system and do quantum measurements on it. Yeah. We're going down a big rabbit hole now.
Okay, let's start. Hi, Markus.
Hi, Daniel.
Hi. So, hi, everyone. So let me summarize why we're here and what is going to come. So this is another episode of what we call the Dialogues on the Foundations. And it's part of an initiative on the foundations of physics from the Center for Advanced Studies at the Ludwig Maximilians University in Munich. And we want to discuss with physicists, philosophers, and everybody interested in the foundations of physics about this cool topic. And it's my pleasure today to have Markus Müller from University of Vienna. And you want to introduce yourself?
I'm a group leader here at this Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences. I'm a theoretical physicist and somewhere in the middle of mathematics, physics, philosophy, computer science, in this kind of ballpark, I would say, yes.
Cool. And I am, as usual, Daniele Riti, and I work at the Arnold Sommerfeld Center for Theoretical Physics. I am indeed a theoretical physicist, and I work mostly on quantum gravity and more generally foundations of physics with some philosophical interest as well. So let's start. If you have heard, not you, Markus, but everybody else have heard about the quote from Feynman that nobody understands quantum mechanics. Well, Markus does. And so I will ask Markus to tell us what he knows and what he thinks about quantum mechanics, including the things that, in fact, I would say nobody really agrees on. And so I'll be happy to hear your opinion. So let me start. So this is a foundations of physics context. So quantum mechanics is obviously a basic ingredient, a pillar of the foundations of physics, simply because it's the core, one key ingredient of all modern physical theories for in fundamental physics. Why would you agree, as I do, that it's also a challenge to the foundations of physics, in the sense that there are many aspects that are yet to be understood, and are also suggesting that we may revise our understandings of the foundations of physics?
Yes, I agree. I mean, you can call it maybe a challenge in the sense that it's just very counterintuitive. So it goes in many ways against the intuitions that we tend to have in our everyday world and our everyday life, and even in our training as physicists who know about Newtonian mechanics, for example. So in this sense, quantum mechanics is just surprising in many interesting ways. And that makes it certainly harder then to find our way in physics to build new theories that are consistent with it.
So in many ways, it's not just, and we speak out of our training as theoretical physicists, the hard part was not just to wake up early, go to lectures, learn to do new calculations and new tools, mathematical or physical, and learn things that we didn't know. It was really, at least from my perspective, for what I remember on my student days, it was really that in many of the quantum mechanics lectures, there was something that just didn't make sense. I couldn't square it with my picture of the world and whatever else I've learned up to that point. Was that your feeling?
Yes, that was my feeling as well. And it was somehow it was hidden in all this kind of jargon that you learn, right? So certainly you learn after a while, you know how to do calculations in quantum mechanics, you know how to calculate the energy spectrum of an atom and so on. But some things are just not said, like, oh, you have this wave function, but then what is it really? It satisfies a wave equation, but what does it mean? Oh, and it's clear that nobody actually really knows, I would say, in some sense. But this is not really said when you're in a beginner's quantum mechanics lecture, I would say. Even if they just said that it's somewhat unclear and controversial, or, talked for one or two lectures about the meaning of it all, then it would have helped.
Mm-hmm. Yeah, and that's where the foundational aspects enter. And I would say that's also where, as theoretical physicists, we are almost forced, if we were not already so inclined, to talk with philosophers and try to see, the issues of the interpretation of what we are doing when we do calculations in quantum mechanics from a broader perspective that touches on a number of more philosophical and, sorry for the physicists who are listening, but ontological issues and metaphysical issues and the like. Would you also, is it also your experience that philosophers have to be there in the room?
Yes, I agree. So, yes. So still, there's sometimes a feeling that there's a big tension somehow between, say, mathematical physicists and philosophers, where one camp says maybe the other camp is not so important or doesn't take each other seriously in a way. I think this is not helpful. So I think one can put these perspectives together and then learn something, and philosophy is an important piece of puzzle. I agree with this. Yes.
I think that this becomes immediately transparent even to the most, anti-philosophical physicist that tries to see everything just in terms of some new calculations to be done. It becomes immediately transparent the very moment we try to summarize, what is it that we learned and what is it that turns out to be the case in quantum mechanics, even from, what is the least philosophically loaded position, which would be a more instrumentalist type attitude in which, I go there, I do something in the lab, some result comes out from my measurement apparatus, and that's it. That's more or less all I'm doing. First of all, as I say to many of my friends that try to avoid philosophy, this itself, the fact that you take this attitude towards what physicists do in the lab and so on is a philosophical attitude. And in principle, if you're serious about it, you're supposed to justify it, and that becomes a philosophical argument because it's a philosophical position that you have to defend against other philosophical positions. So you're not really avoiding philosophy anyway. But even in that case, since what comes out of our measurement apparatus tends to be, as you said, quite counterintuitive in many ways, you still have to wonder if your conceptual scheme has to be adjusted. I know that you work a lot on exactly this more operational, if not, instrumentalist way of addressing things. But I also know that you are keen on philosophical considerations. So clearly, you also feel that taking operational attitude doesn't free you from philosophical considerations.
Well, I would even say it overlaps very strongly. So if you're a diehard operationalist, you might still be interested, for example, in having quantum cryptography or a quantum random number generator, no? And then you can work out with all the equations of quantum theory that if you do it, you do measurements on an entangled state, and then you get outcomes, and then nobody could predict those outcomes. Now, why does it work? Is there a way to understand why this works, or what the basic or main ingredients are for that? And then you can say, well, yes, in some understandings of quantum theory, for example, the outcomes that you measure are just not predetermined before measurement. If they are not predetermined, then nobody can eavesdrop on them. So you get immediately some kind of understanding why the things work when you try to understand a bit better what's actually going on, which overlaps certainly in a strong way with interpreting the quantum formalism.
So to some extent, even from the more operational point of view, you cannot do without understanding what's going on, at least to some extent, and understanding starts bringing in questions that are of more conceptual type. I mean, the first thing you said that the outcomes are not predetermined. It's already extremely counterintuitive, because if we think about classical mechanics, the naive picture that us physicists learn is that okay, there is a world out there, and so far we can still agree also in quantum mechanics, and that we just find out what are the properties of various material systems by just looking, which is in a broader sense, performing a measurement. And then we find out what the position of the object was, what the color of something was, I don't know. I mean, whatever was the property we decide to, investigate. And somehow in quantum mechanics, exactly according to what you said, that this seems not really to be the case, at least not in this obvious manner.
Yes, right. Yeah, that's the fascinating thing. So that this impossibility of holding such a view is actually provably the case. Yeah. So according to Bell's theorem, it just cannot work that you hold such a view. No. So when you say that, I just believe in the world out there as being this stage that's just sitting there with objects, and these objects have properties, and the properties are just fixed. Maybe they change over time, but they are there, regardless of if or how anybody measures them. Then you can say, well, any world that satisfies this would have to satisfy also the Bell inequalities, if we believe a couple of other well-motivated things about the world. And then we go to the lab and find that they are violated. So the exciting thing is that this is now more than just an opinion, right? It's a theorem in some sense.
In fact, okay, let me give another piece of reassurance to whoever is listening. I mean, not only Markus is a theoretical physicist, and okay, me as well, but he actually proves theorems. And people in foundations of quantum mechanics actually prove theorems. A lot of progress has come by proving theorems on the basis of assumption, in which, of course, you encode some more philosophical, condition or desideratum. And so foundations of quantum mechanics and foundations of physics in general is a science in any sense in which you want to define a science, including the rigorous mathematics to the extent in which it's possible to prove things. As theoretical physicists, we don't always prove things. Normally, if you can prove something, you probably simplify the problem too much. But in some cases, like in foundations of physics and foundations of quantum mechanics, that simplification is exactly, distilling out the key elements that you want to put in correspondence and you want to test.
Yes.
So you mentioned Bell's theorem. Let's start from there. So let's take a step back from Bell's theorem. And for what I know, I mean, Bell's theorem is the best way we have to put to test or formalize the issue that was raised before by Einstein, Podolsky, and Rosen with the so-called EPR paradox. Do you want to summarize very, very briefly what that is, and then we discuss?
So yes, so the EPR paradox was put out in 1945 by the physicists that you mentioned. Einstein is one of them, Podolsky and Rosen. The idea is, like in Bell's theorem, many of the setups, you look at two particles. So they begin are produced somewhere in the middle, and then they're sent to two very distant locations. Now, what you can do is, so what happens sometimes is if you get that these particles end up in an entangled state. Entangled state means that some of the properties are linked to each other in an interesting way. So you could have this classically to begin with. You have two shoes, a left and a right shoe. You put them into boxes, you shuffle the boxes around. You give them to distant laboratories. When you open one box, you find a left shoe. Immediately that you find in the other box has a right shoe. So this is just correlation. Now, what EPR observed is that with quantum particles, you can have similar correlations when you send them to distant particles, but in very surprising ways, or in ones that seem to be contradictory to begin with. No? So one thing that quantum theory, for example, says is you cannot measure position and momentum at the same time. So when you know the position of a particle, then you don't know its momentum. When you know momentum, you don't know its position. But what they considered was a situation where you measure position of one particle, and then you immediately know the position of the other particle. But if you do it for momentum, then you immediately know the momentum of the other particle. So it seems like from a distance, the particle has decided what stance to take, what position to take. So as if there was an action at a distance in some sense. And that was termed the paradox in that paper.
And also the point was that, if I remember correctly, you can play about this you can play with this correlation by saying I measure the position of one, so I know what the position of the other is without measuring it, but then I can measure the momentum of the other one, and I know what the momentum of the first one was. And so somehow I got to know both the position and the momentum of both particles without interfering, without any contradiction with the Heisenberg uncertainty, with the impossibility of measuring both position and momentum. So I'm using quantum mechanics, but I seem to go beyond and violate basic constraints that I have in quantum mechanics. And so they were arguing that, okay, this must mean that quantum gravity is not the final theory. There must be some way to complete it. Clearly, it doesn't contain all the information. And Bell's theorem is a way to sort of formalize this in a way, in a more general sense. Is it correct? I mean, I'm not misunderstanding.
No, I fully agree. So I certainly know stuff about Bell's theorem, so I haven't even read the original 1935 paper, I should say. Read lots of people writing about it, but it would take some time to actually read it. Well, but when you look at the thought experiment, you might say, well, maybe it's not that compelling. So, you have this one counterintuitive prediction of quantum theory that you cannot know momentum and position at the same time. And you embed it in another more counterintuitive thought experiment, and then you have a clash of intuition. Oh, well, the theory was counterintuitive to begin with. But Bell's theorem is really a step forward in the sense that it doesn't really rely very much on the quantum formalism. It just says that here are two things that we believe very strongly about our world, which is locality and realism. And once we believe these things, then in any experiment of that sort, we should see a certain type of correlation. Correlations that satisfy the Bell inequality. Now you go to the lab and this inequality is violated, which tells you that one of these two metaphysical assumptions must have been wrong. So either locality or realism, or the very framework in which you formulated it, which is another way out.
But the point of the framework, if I remember correctly, says, I mean, it's sort of a statistical analysis of correlations and probabilities. It's, of course, there may be ways of generalizing that, but it's hard to do. It's that was also counterintuitive.
Yes. So the assumptions are extremely weak. No, so some people make the mistake and try to disprove Bell's theorem. Here's a scheme how I can do it. Like, no, you cannot do it. So in any conceivable world where you think of stuff is distributed, it's in some actual state. Maybe the state is unknown. Something that computer scientists would call shared randomness. As long as it's formulated in that way, you can derive the Bell inequality. So I'm simplifying a lot. I'm certainly dropping a lot of the discussion about the fine print that goes into the derivation. But it doesn't matter what you send. It doesn't matter that space is 3 dimensions and what other laws of physics hold. It's more in any conceivable world where the framework, say, of standard probability theory holds, and you can set up a particular causal sense scenario, you expect these correlations to satisfy Bell inequality. So yes, very, very weak assumptions.
So let's say it's more about the two main assumptions that somehow seem to be clashing with the experimental results and following the violation of Bell's inequalities. So you said is locality and realism. So let's say that realism is just the sort of picture that I was the sort of intuition I was suggesting earlier, that I was mentioning earlier, in which there is a system with its properties. They may even be probabilistic, but they are there in the system. In fact, in this case, you have two systems that are somehow related to one another because they've been prepared together. But they maintain, first of all, the individuality. So you can sort of separate what you can say about one system and what you can say about the other. And so you can individuate, characterize independently the two systems. And then realism means that they have some property. And then indeed you find out by performing measurements at the later stage on the individual systems. And then locality, again, to summarize, is basically the point that, you interact with the system locally, your measurements are going to be local, and there's no, instantaneous transmission of information so that, you interact with your system locally here, at the given time, and somehow when you interact with the system here, the other system that had previously been correlated with this is modified by what you're doing here. So this is the intuitive notion of locality that is in Bell's theorem. And the strong point is that somehow we need this type of assumption because to some extent, otherwise it's very difficult to do any physics. Because the other system, the two systems could be very far away. Literally, one could be here and the other one has been sent to the other side of the galaxy. And so if this assumption of locality was not true, it means that now I interact with my particle that I prepared in the lab and I keep in my lab. The other particle that I prepared together in a correlated entangled state now is at the other end of the galaxy. And by manipulating my particle here, I am literally instantaneously manipulating my particle on the other side.
Yes, so what I think one should really, for everybody, make it clear that signaling is forbidden. So you cannot use the setup to send information faster than light. So what you could do is exactly what you said, Daniel. You could say one of the physicists is now on Earth and the other one's in Andromeda galaxy or very far away. And suppose they share such an entangled state, then they cannot use these correlations to send information. Otherwise, it would contradict relativity and allow them to send information faster than light. But quantum theory forbids this right away, even without using relativity theory. So there cannot be signaling. But you can say, if I wanted to simulate this behavior of the entangled particles with classical stuff, with coins or messages that are read on pieces of paper or other stuff that I can describe as random variables of probability theory, and they are embedded in the causal structure that I described. So you have some common cause in the middle distributed to the two agents, and they just act independently, make independent choices, and then they get some outcomes. Then to simulate that classically, you would need instantaneous information transfer between the two. So again, it doesn't mean that once you have this quantum behavior, you can get this information transfer. No, you cannot build a Bell telephone and you cannot signal with it. But
so how do you check that the particles are correlated? Indeed, that maintain this correlation. You do independent measurements, and then you later on you check, you confront the measurement results that have been performed independently.
Yes, right.
So it's like the two of us do independent measurements on our. Me on one particle, you on the other, that we prepared together in the lab some time ago, and then we kept somehow in some entangled state. That's the difficult. That's the difficult part. So I do all my measurements, and I decide independently from you, without communicating, what I measure. What type of observable. Is it the spin in this direction? Is it the position? Is it the momentum? Is it the spin in some other direction? Some intermediate thing? I do my list of measurements. You do the same, and I don't want to know what you measured.
Yes.
Then we meet hopefully soon at some party.
Yes. That's the important part.
Yeah, okay. This we don't need to go into details, but yes, we're going to meet.
Yes, you have to meet, no? Exactly.
And I brought to the serious scientific meeting that we are meeting at. I brought my list of measurement results for my particle, and you brought yours. We compare.
Yes.
And somehow we see a perfect correlation between the two type of measurements. A bit similar to what you said about the one shoe and the other shoe being necessarily correlated in a specific way, but according to the more complicated rules of entangled states in entangled systems in quantum mechanics. And this perfect correlation does not satisfy the mathematical properties that would follow from the two assumptions of locality and realism.
Yes, indeed. Again, locally for you, Daniele, certainly, or for me, I wouldn't see anything of what you're doing in my data. I would collect my data in my laboratory. There are no traces whatsoever of what you do. I cannot infer anything about your choices. But then when we meet later, that's why I emphasize so much the meeting part, we compare the tables, put them together, and then we find, wow, this is really a data table. that they could not have been simulated with these pairs of shoes that I send around. So no signaling as long as we're far away, but some big surprise when we actually meet in the middle. And
the properties of these correlations, as you said, they cannot be simulated by any classical type of correlations or any. In fact, I would say even more. If I understand correctly, is no model that satisfies like classical mechanics does, but no model that would have inbuilt the two assumptions of predetermined values of the properties. That would be something like realism, and locality would produce those correlations.
Yes, maybe a minor reservation without going too much into detail now. Perhaps we can do that later, but there's work by Gilles Brassard and Raymond Robichaud, Paul Raymond Robichaud, for example, where they say, look, we can have locality and realism if we give up the hidden variables framework. So the hidden variables framework tells you that there's stuff in actual states, the actual configurations that you send out. And what they do is they give up this framework and they have some kind of many worlds-like picture where in your laboratory, when you do your measurement, you actually split up into two Danieles, and I split into two Markuses, and later we meet in the middle. Only one version of Daniele meets with another version of Markus in such a way that the correlations are reproduced. So this is something you can have, which I think is really interesting, which tells us just we have to be a little bit careful. So it's locality and realism as formulated in the what's sometimes called the ontological models framework or the hidden variables framework. This is just not tenable.
Or if you want, in a single world.
Or in a single world, yes.
So, well, in any case, it should be clear from the little we said, first of all, something very intuitive and I would say very profound in our picture of the world has to give in. I mean, that something has to go, and it's up to us to decide what and to build further foundations of physics on that basis, or if you want, without that ingredient. And so what's your choice? The way you presented earlier, I would assume that you're more inclined to some weaker form of realism rather than dropping locality. But I've heard
yes,
very different opinions.
Well, yes, I think, I mean, I try to be agnostic up to a certain point and not make too clear of a stand because there's so many things I don't know. But I guess I would subscribe to a view where I give up on a naive version of realism. This naive version that we have this world where there's just stuff that's sitting there in well-defined properties. I would give that up. I would not, the other option would be that you, for example, like in Bohmian mechanics, you say, oh, the world is like that. There's stuff sitting there with well-defined properties, but there's actual superluminal communication between Daniele and Markus in our experiment. I would say no. This would mean that I try to explain. So I find this implausible. Maybe I can say it later, or we can talk about why this is perhaps implausible. They would say no. Maybe the world is different. So I can be a realist without subscribing to hidden variables. For example, there's a notion that's sometimes called structural realism or ontic structural realism, which says that yes, in some sense there is a real world out there, and it's not a miracle how that we see these regularities in our data. There's actual stuff sitting here in some sense, not in sense of matter or things, but of structure. And so there are in some sense real patterns in our observations and mathematical structures that are real. And not so much stuff like colliding billiard balls.
I see. So the opposite point of view that I've heard is somehow is the one that is most, I would say, is most well known, because when you hear about what Bell's theorem says, or just what is the main lesson of quantum mechanics, or one main feature of quantum mechanics, very often the answer is straightforward. People say, well, we found out that the world is non-local and that quantum mechanics is non-local, and that's it. I mean, there's no way around it. And what you're saying, and I have to admit, I don't know who else I will be talking to in the next episodes, but maybe I will have to regret this, but I tend I tend to agree that it's more plausible, although still counterintuitive, to drop this naive, simple-minded realism. Despite the fact that we built on it most of our physics until quantum mechanics. So you would clearly not agree that quantum mechanics is non-local in any obvious sense.
Yes. So maybe two things to be said about this. So the first thing I guess to say is that some of what you describe can just be a confusion of terminology. So there is a community within the field of quantum information that I'm also part of to some extent, where they study, for example, how what they call Bell non-locality can be used for certain tasks, like having quantum cryptography, building random number generators that nobody can predict, and so on. And the word non-locality is used there, but the way people look at it is to say, certainly there is no superluminal transfer of anything. Non-locality just means that it's that kind of weird data that I measured. And that weird data that I measured certifies that the actual outcomes that I've seen have not been predetermined. That's why I can build the random number generator in the first place. There's this very, very strong intuition that it hasn't been predetermined what has been measured, and there is no superluminal signaling. But it's still called non-locality more due to laziness, because how you should give that some name, these correlations, so you call them non-local.
Mm-hmm. So to some extent, one could say that you can, indeed a bit of a misnomer, but you can call non-locality the very fact that there are correlations between two systems which are maintained even though they are very distant from each other. So in that sense, there is some form of non-local, indeed correlation between two things. But it doesn't mean that there is an influence of one to the other, like a cause-effect relation, for example. Or some signaling, as you said, that is also not the case. I was speaking with Jenan Ismail, and the way she was posing the issue was to some extent neither exactly a weaker form of realism nor non-locality in any spatio-temporal sense. She's keen of calling the issue non-separability, so which I would say is the issue with realism. So remember when I was discussing the way I was phrasing the PR paradox and Bell is the fact that you have two subsystems which you can individually characterize with properties. Those individual properties is what you measure locally for almost by definition. You only have access to your system in the lab. And so she would say that a good way of interpreting what's going on is that the moment two systems are entangled, this is only a very partial characterization of what the actual system is, which is the pair, the two systems being entangled and correlated. So in that sense, you could say that quantum mechanics is non-local because you say, well, the real system is actually stretched across the universe because these two particles are correlated. So I cannot really separate the two in more ontological manner, so to say. And but it's also a weaker form of realism because this idea that the individual systems have their own independent reality is part of what we mean by having a reality for the subsystem. So I think it can be seen both ways, and so even if you call it non-separability, you fall back in the need to be more precise. Is it non-separable in one sense or in the other one?
Yes, you can. I fully agree. So you can have this view this strikes me as a very nice picture of how to think of entangled systems indeed, no? And when you call that then non-separable or even call the correlations non-local, this doesn't entail directly a claim that there must be underlying superluminal signaling.
Really?
Yeah.
But I mean, there are hidden variable models or like Bohmian mechanics in which you can also be compatible with non-signaling, as far as I understand, at least with the experimental bounds on non-signaling. Mm-hmm. But if you just look at the equations, there is an obvious sense in which the underlying particle positions are correlated at any given time. So in that sense, it's clearly a non-local theory, although is still there is no signaling at this level.
Yes, and I mean so to speak, the implausible. So what I see as an implausible aspect of these theories is a version of fine-tuning. So in the fundamental laws and equations of the theory, say of Bohmian mechanics, you have a built-in superluminal information transfer. Like particles just move faster than the speed of light. Now you get a statistical averaging effect in some sense, so that you don't see it or you cannot really use it for signaling, but the theory is deliberately built in a way to prevent this. So it's like you introduce these invisible angels and demons that are supposed to push your particles, but then you hide them deliberately, right? So, and you see this, for example.
Can I interrupt this? Do you have many Bohmian friends?
I have some Bohmian friends, for example.
No, I don't want to know. It's just that this characterization may upset some of them.
No, because I was just about to mention him, because that's not what he does. So what Valentini does, for example, he says, let's not have the fine-tuning. Let's write down the equations and not tune them in a way that would forbid superluminal signaling, but let's bite the bullet and say, this is now my hypothesis of nature. And then perhaps sometimes I can have some version of signaling. It's just that after a while, this equilibrates and then it gets into the status that's described by quantum theory. So this, I think, is really a good approach. So this is something I like and find interesting, that you say, yeah, maybe then let's try this realistic approach and let's bite the bullet and say what would be the consequences of superluminal signaling and actually predict some situations in which I would see that, and then explain a mechanism for why it becomes usually impossible. This strikes me something much more convincing than just postulating right away that it's invisible.
You're right. I mean, maybe if I can, I would say that also when we said that Bell inequalities are violated, and that's a fact, that's an experimental fact. I mean, the way physicists deal with this type of facts is that any experiment would only give you constraint on what is possible, and it doesn't really rule out anything ever. You just have to be clever enough and to understand what sort of model will still, maybe keep the hypothesis that you wanted to rely on, but be compatible with the bounds or the constraints that you found observationally. That the inequality maybe doesn't. You don't have to have an inequality, but you have to still have a violation. They have to be closer to the bound found in experiments, and so I just want to say that physicists, especially theoretical physicists, you can say the positive way. We can be very creative in devising ways of explaining things or being compatible with both our theoretical assumptions and the experimental constraints. You can phrase it the bad way. I mean, we can really hold to our disproven theories, no matter what, just finding a way to keep, our assumptions because we like them.
Yeah. Yeah.
It's just a matter of honesty in a way, to just have to be honest about what the observations have told you, and you cannot pretend that they can be ignored.
Yes, exactly. Yeah. It also seems to me some kind of general attitude. I mean, shouldn't we be prepared to be surprised? Isn't it a good thing that the world is different from our intuitions? I mean, if the world was just as we expected right away, right, stuff colliding and whatnot, probably wouldn't have gone into physics because it would just be so boring. Right?
I agree.
So many times, so yeah.
It would be such a boring and useless enterprise that, frankly, I don't know if it would be me getting bored first, or people decided that they don't need to pay anybody to do it.
Yes.
In both cases, it's bad.
Yes, exactly. Yeah.
Anyway, so if non-locality or non-separability or some dropping realism was not enough as counterintuitive possibilities. The other thing that quantum mechanics is told to be is contextuality. So normally people say that quantum mechanics is contextual. What is meant by that?
So yeah. So there are different.
It's complicated. I have a lot of trouble explaining it to my students when I.
Yeah, it is hard to explain. The problem is there are different versions of contextuality. The one that I find somehow easiest, well, maybe not easiest to explain, but most convincing is the one that Rob Speckhans has put forward. It's sometimes called generalized contextuality, and it's a notion of fine-tuning. So, for example, when you go back to Bell, as we discussed before, you can say, well, if I have a view that there's actual superluminal communication, I just don't see it in the data, then you need some fine-tuning that exactly washes away the signaling so that you don't see it in the data. The parameters of your model must fit that to make this effect exactly 0 and not 0.1 or minus 0.1. So, yeah, and that's somehow, some people see this as implausible. And contextuality is another way of formalizing this, where you not necessarily have two parties, but just a single system, your physical quantum system. And you think of states and measurements on that system, and then you think of perhaps some classical explanation of the statistics.
Mm-hmm.
And you say that a classical explanation would be plausible if it's not fine-tuned. So what do I mean by not fine-tuned? Well, you can think of a quantum, say now you have a particle, an electron, and you have another electron, and maybe they're in the exact same state, just differently prepared. So different ways, for example, to preparing it in a fully mixed state where you cannot prepare anything. Like you toss a coin and then with 50-50 probability you prepare spin up or spin down. And with the other particle, you would toss a coin and with 50-50 probability you prepare spin left or spin right. Now, quantum theory tells you the results are completely indistinguishable for all measurements that you can do exactly the same. Now, what non-contextuality tells you is that if you think of some classical underlying hidden variables, they should also be the same. They should also have the same statistics. And this is actually the reason why the quantum systems have the same statistics ultimately. It's because the underlying variables, the classical ones that we don't see, are the same.
Mm-hmm.
I can show that this is impossible. There is no such model. And in some cases, exact same quantum states, just differently prepared, need different classical underlying descriptions. And that's, again, an implausible notion of fine-tuning.
So somehow the issue becomes that once more that of realism. So is the idea that there are some properties of the systems, quantum mechanics partially accounts for them, and then you want to say that all these, all these results and mathematical and observational just put constraints on the relation between the quantum mechanical description and what you can actually assume was the underlying hidden reality. And tells you what you're allowed to believe or not, in a way. So you're always free to postulate that there is something hidden and beyond what quantum mechanics says. But all these results, Bell and the results about contextuality, basically tell you, yeah, you can always do that step, but your underlying reality should at the very least have such and such properties. You cannot say whatever you like. I mean.
Right, yeah, exactly. All these theorems tell you this underlying classical reality, yes, it's possible, but it would be really a weird place. I mean, we have other theories, those like thermodynamics, the science of temperature and heat and so on, and we understand that this is just an approximation to an underlying theory of statistical mechanics where particles are colliding and so forth. And now, here the relation going upwards from statistical physics to thermodynamics is really a coarse graining, and you can actually show that it's non-contextual. You don't need any kind of fine-tuning. It doesn't matter what you exact find. If you have the same temperatures, you can, if you want, have the same distribution over particles. Right? So this tells you that you can have some notion of plausibility or implausibility. You say, how about a possible underlying, more microscopic classical theory? Is it plausible to assume that, yes or no? And then contextuality would be to say this is a notion of implausibility. Again, plausible, implausible is a matter of taste, but still you can prove that this is a feature that you need to have. No.
So it should be clear by now why there are many interpretations of quantum mechanics, many perspectives that people can take. Because, there's one thing that everybody agrees, which are the predictions of quantum mechanics, the way we use it, the way it has to be used, and is the stuff that you find in textbooks. The stuff we learn. And on that side, everybody agrees. Then you can start asking, okay, but is this the story, or there is some hidden story to be told, and quantum mechanics partially reflects that? So first of all, some people say, no, that you don't have to postulate anything else, so just try to understand what the theory is about. Don't try to force any intuition from classical mechanics in some underlying, hidden level. Okay, but even if we agree as an hypothesis that there is some underlying hidden level of reality that quantum mechanics doesn't fully encode, the agreement is that this other level is going to be super weird anyway. So it doesn't save us. There's no way we save the classical mechanical intuition about what reality is in light of quantum mechanics. One way or the other, some weird ingredient has to be there. And then the disagreement and different interpretations and so on is, also what is this weirdness at the more, hidden level. Sorry, I'm making fun a bit of the debate in the community, but, more or less, would you say that that's the case, or am I totally busy?
Well, I fully agree with what you said, right? So in a way, I think quantum foundations research is extremely interesting. But then sometimes it's a bit the question also, what do we really want to achieve? And so what's perhaps not so fruitful is to kind of argue between two possible interpretations that made the exact same predictions and just do that. You may want to argue on the basis of saying, I have unresolved problems in physics, maybe quantum gravity or other problems, and maybe one of the views on the exact same predictive formalism allows me to make more progress than the other, perhaps. Then it's clear. But if it's all this you're doing is that without really showing anything and proving any interesting theorems, then I think it can in many cases be very unfruitful.
I see. So that before we move in detail to this, what could be consequences of a given interpretation, or what is more technical advance or physical advances that are made possible by reflections on the foundations of quantum mechanics, and if not interpretations. Let me hit on another big problem in the foundations of quantum mechanics. In fact, it's the problem that a lot of people first encounter when they ask around, what quantum mechanics means, and is this, the whole idea of the measurement in quantum mechanics and the wave function that somehow poor thing collapses whenever we look at the system. I always felt a bit sorry for. No, I really was not inclined to go in the lab and do measurements and so on. But when they told me that whenever I look at something and do a measurement, the wave function of the system collapses, I felt even worse.
So wave function.
What is all about? What is it that collapses?
Well, yeah. So you know very well, but for the others, so when you look at the textbook postulates of quantum theory, then it tells you that physical systems are described by wave functions, and then wave functions just evolve in time according to the Schrödinger equation. It's a bit like what particles would evolve according to Newton's laws, continuously in time and deterministically. So when you know the wave function at one point in time, you exactly know what it is at a later time. Now, this is true except at the moment when there is a measurement. So this is another postulate from the textbook, Postulates of Quantum Theory. you do a measurement and then suddenly the wave function changes discontinuously. It becomes what's called an eigenstate of your observable. So, you measure spin, and then instead of being a kind of wave function over all possible spin values, it picks one of the spins and then becomes localized only on that value. And that's the value that you learn. So you have these two conflicting ways in which that can, in some sense, happen to a physical system. And this raises many questions like, what is a measurement? How do you know that you actually did one? Or is that, and so on.
Some of these are the questions I was asking to my, tutor in the lab.
Right.
How do I know that I've done a measurement? What am I supposed to be doing here?
Yes.
I can turn serious at some point. The serious look. Please keep going.
I will imitate this now. Yes.
Serious look.
Yes.
Okay. So the issue is that the generic quantum system, the way we describe it is that a generic configuration of the systems, a system, say, for which we can measure the position or the velocity or the spin in one direction, a generic situation, a configuration which the system can be, and then can be described by the mathematics of the theory, will be some, superposition. So it's some undefined state that is neither in a given position nor in another. So it's somehow all possibilities are accounted for. And there is some probability that if you measure, you will find it in one situation or some precise position or with some precise velocity or some value of the spin in a given direction or another. But the theory just says generically, however you prepared your system, it will be in some indefinite situation with respect to any observable you may decide to measure later. But then, of course, it's a fact that, okay, not mine as a theoretician, but of whoever goes there and does the measurement, that the measurement apparatus will give you a number. So some precise value for whatever you decided to measure. And so this is the sort of tension that, as you said, is resolved by this postulate that, the state of the system, the wave function, when you perform a measurement, falls into one particular configuration, one particular value for whatever observable you measured. So, and these two things, as you said, they don't really, right? They are fine. They coexist because we use them in the right situations and results are okay. It seems quantum mechanics works and we predict a lot of interesting stuff, but they're clearly strange. I mean, it's like there are two different ways of for a system to be changing in time, to be evolving, and so, what's your solution? What's going on?
Yeah. Okay. I mean, I guess the only thing you can ask for is what is my view on quantum theory at the moment, and what would then I at the moment want to say about this.
I'm also happy if you say, look, I haven't decided, but these are the 2-3 possibilities that I'm considering. And
yes, so I mean, one thing, all I'm saying here might be completely wrong. So I had to change my opinion if some other person has good arguments at some point in the future. But it seems to me that this so-called collapse of the wave function is best interpreted as an analog of just belief updating. So in classical probability theory, if somebody, shakes a die inside a glass or the glass, what's it called in English? You play a game and you have a die.
Box.
Pardon?
Some box.
Box, yes, certainly. Thanks. So shakes it, but doesn't look at it and then gives it to you. And now you would say, well, what state do you assign to the die? Well, a kind of probability distribution. Probability 1/6 over each side, right? And maybe the die is actually rolling around and hasn't landed yet. And so there's a kind of equation that tells you, like, if you had a higher probability for 6 now, then it maybe turned around, it became a higher probability for 1. So there's some time evolution going on. But now if you look at it, then you suddenly actually see the outcome. So you learn new information. And then what you have to do is you have to update your beliefs. now this probability distribution is not anymore your description, but you actually know what's going on. Also, if somebody just tells you, oh, by the way, it's an even number, then you would update your beliefs and assign probability 0 to the odd numbers and uniform probability to the evens. So I think the so-called collapse of the wave function, and that's really an advantage of a certain class of interpretations of quantum theory, which I think in your paper you even dubbed the pragmatic ones or epistemic ones, is that a quantum state, when you see a quantum state as something like a probability distribution, then it's not so surprising that on measurement you have something like a collapse or an instantaneous change, because all the changes is basically the probability assignments given new information.
So to complement what you said, I mean, when in quantum mechanics, the textbook says, the system is assigned or is associated to some quantum state, some wave function. Now, the big debate is to some extent whether that thing, that wave function, the quantum state, is, as I was initially presenting, it's a statement about the system. The system is in a given superposition of different values of the position or the side of the dice. So it's something about the system, a property of it. Weird, because to be in a superposition of different possible values of the position is pretty weird, but still, it's a property of the system. If that's the case, then this collapse of the wave function is truly weird, because then it really means that, just by looking at the system, somehow the system suddenly changes in its own physical properties to something specific. Something definite. It's not impossible, but it's indeed very difficult to square with how the system is supposed to evolve, and then you have to explain what exactly counts as a measurement and so on, because what sort of interaction is simply two systems evolving together with their own quantum states, and what other type of interaction I call measurement and produces this sudden collapse to a given value. The other possibility is what you described. I mean, maybe this wave function or the quantum state doesn't have to do with the system, or it is not only with the system, but it has to do with our knowledge of the system, or our belief about the properties of the system, or our expectations. And then indeed, as you said, as in classical probability theory, it's not strange that you first hold a certain belief or a certain knowledge about the system, then you look, or you simply interact with the system, and necessarily your belief have to change because the information you have now about the system is different. So this sudden collapse is not a physical process, is a sort of knowledge step. Or now also this is debated whether you can really talk about knowledge. It brings a number of other issues, which indeed I'm going to raise.
Okay.
Raise yourself.
No, I mean, yes. What is that? No, you want to add something more? Sorry for interrupting.
No, I just want to make sure that you're comfortably seated and you're now ready to answer the other question.
Yes. So let me say one thing. So what you said about the quantum state, no? So it is just a mathematical fact that the quantum state is uniquely determined by the list of all probabilities of all possible measurements that you could do in your system. So there's a one-to-one correspondence between quantum states of some fixed system and the possible probabilities that you could see in experiments later on, right? So this tells you that it is consistent and possible, at least, to see the quantum state as the same kind of thing as a probability distribution in some sense. It even embeds in a mathematical framework of general theories of probability, where our usual probability theory is just one point, but there's another one that's called quantum theory. Similarly, as you say, there are different theories of geometry. There's just the usual intuitive Euclidean geometry, but there's another one which is the counterintuitive Minkowski geometry of special relativity.
And that's just the beginning. Yeah. With geometry and possibly also with probability
Yeah.
So indeed, but what I said about the second option, and which is I was re-expressing what you said better than I did, but it brings unfortunately a bunch of other issues. So it's a solution of the collapse thing, because you say, look, I mean, all these problems about what sort of physical process is the collapse, the wave function is just a misunderstanding. They're just the wrong questions. You're just updating your knowledge or your beliefs and so on. But then you fall into another bunch of issues, which is, but then, in quantum mechanics, it's necessary to have an observer. The theory is not about the world, it's about the observer. It's about whoever uses the formalism to do measurements and compute things. And so somehow it is not a description of reality, it's or of the world. It's more an account of what is in our minds, and that's it.
Not necessarily, no. No, not necessarily. So, I mean, what it tells you is that the quantum state is not a description of a world as we usually imagine. Again, if we imagine a world as a collection of things that's sitting there that have certain properties, more concretely, some material stuff somehow that's characterized by fixed values of stuff. So when you take a view on a world that is more along the lines of structural realism, then this gives you the option to say, well, maybe the world is essentially probabilistic structure. So what we call the world is essentially that thing that determines somehow the chances or the propensities of what I see or what happens to me. Mm-hmm. And then certainly, classical probability theory might say, well, but it's, where are they encoded and what kind of objects? And where do they come from? But you can say, well, maybe that's the wrong question to ask. Maybe probabilities are just fundamental.
I see that. But it remains true that you have to drop, again, this pretension that we inherited from classical mechanics that indeed the world sits out there independent of anything else, we just find out. So it's the probabilistic aspect, but indeed in quantum mechanics it would seem that this assignment of a list of probabilities has to do with, well, us or whoever is the system that plays the role of observer in a particular case and decides to assign certain wave functions or certain quantum states. So it's still, in a sense, is again in the direction of a weaker form of realism, or at least going beyond any naive form of realism. So the observer may not need a PhD, luckily. It doesn't even have to be fully conscious, but at least should be able, if it concurs into the assignment of quantum states, to reason in terms of probabilities or to have some influence somehow on the reality of the system we are talking about. I mean, there is at least some relation between the system and this whatever is playing the role of observer.
Yes, I mean, so certainly, as you said, like that. Conscious observers or humans have no fundamental role in quantum theory. I strongly believe this. But there's some notion, something that we like to call observer that seems to play a primary role. And I agree, this can be something very basic, but it can be even more basic perhaps than what you said. I'm really thinking of just whatever you have that records outcomes, for example, that you can interpret as recording outcomes or collecting data and doesn't have to be alive or conscious or not even be able to use quantum theory to predict. You could still say then, if it could use, then it should use quantum theory to predict because it would give the correct probabilities, giving the previous findings to predict future outcomes or so.
Yeah, you're right. I was being a little bit provocative, but there is a whole range of within the broader framework that you mentioned as a way of addressing the problem of the collapse of the wave function, the measurement problem, and so on, which goes in this direction of knowledge-based or belief-based interpretation. There is a whole range, and in fact, it could well be that the only thing you need to call observer is the measurement apparatus, or or some context in which you place your system, and that concurs in determining the state of the system, or the property, and therefore the probabilistic properties of the system. So I don't want to push you too much in one direction or the other. I want to give it more of a range of possibilities. But clearly, yeah. Sorry, go ahead.
No. I was just thinking. So some of the wording that you choose, the terminology that you choose, I think one has to be a bit careful when you say that. Oh, maybe it's the measurement apparatus or so, because in this view you would say whatever the observer is, it's a primitive of the theory. It's not something that we reduce to other material stuff, because that other material stuff is just an epiphenomenon of quantum theory, which just sits on the notion of observer as a primitive. No, so the observer is just a pattern, the outcomes, the recorded stuff in some sense in that view. And the good thing is that we don't have to say much more than that, because whether we treat an actual device on our desk as now an observer or just a piece of matter that gets entangled with another system doesn't make any difference whatsoever for all predictions that we can make. So this is like the variability of the Heisenberg cut. Like, where do we place the cut between the observer that records the data and the rest, which is described by quantum state? It turns out that there's a very strong variability without changing the predictions of the theory.
You're right. So let me see if I understood. So the main lesson, if I don't want to push in any specific direction beyond, pushing the direction of, collapse is not a physical process, is something that has to do with the observer. Well, the observer is whatever it's out of the Heisenberg cut, whatever is not included in the description of the system. And the key lesson is that you cannot get rid of it. So you have to exclude it, you have to leave it out, but what you cannot do is to pretend that there's nothing out. You cannot pretend that you can in fact decide that whatever was at this moment the observer, like myself, can be itself be modeled by quantum mechanics. And if we are super smart, you can do it. I can be part of the system you decide to model, but by doing that, you're leaving something else out, which will play the role effectively of the observer, understood in this more abstract sense.
Yes. But yeah, I still want to think. I think, in one sense, I'm actually with the Aberratians in one characterization, right? I wouldn't say, for example, the physical system here, this Daniele piece of matter, this is the observer, but I would say it's the pattern of your observations, maybe the pattern in your eyes or your brain, or if you're recorded, the recordings themselves. And then the Aberratians would say, well, this may now split up if you get entangled. So I should think of, it's the same piece of matter, but in a superposition. And then I should think of actually two possible different recordings being represented by the two branches. And one recording would be one observer. And that could ask, what's the next recording that I get? So it's more not the quantum matter itself that is the observer, but the pattern represented by it somehow. And since it's represented by your body that's sitting here, I can certainly treat your body as a quantum system and do quantum measurements on it. Yeah. You're going down a big rabbit hole now.
No, it's right. I mean, even when I try to simplify the story as, okay, there is something out of the description of the system, well, whatever is out, I should be able to say, okay, a little bit more what it is, how it can be modeled, how can I move this boundary, this separation between the system and the rest, if I can include more stuff inside, and there are, of course, a number of non-trivial issues. It's always like that, right, in physics. When you may have a very smart solution of the measurement problem, but you are raising a number of other issues that can turn out to be even more difficult or more subtle, and and less intuitive. But now I don't know if I want to ruin our friendship, but by asking something else. But
Right.
I'll take the risk. So the moment we say that somehow, a quantum system is we cannot really say or be content with the simple statement that the system has a certain set of properties and we only find out about them. And we instead say that somehow we take part in the system having certain properties in ways that have to be clarified. And these previous 5 minutes have to do exactly with, we have to clarify all these other aspects and have to be more careful with the words we use and the concepts we rely on. Okay, at the same time, quantum mechanics applies to everything. At least as far as quantum mechanics tells us. So is the moon out there? Is the moon in a given position in the sky, even if we don't look at it? It must have been asked this question by your kid, or once you explained to quantum mechanics.
It was actually asked by a 14-year-old who was visiting me yesterday morning, who was doing a school internship. And I told him about all the stuff with Bell's theorem, and then he asked me, is the moon there when nobody looks? And
run away, or you answered?
I answered. I said, yes, of course. So in a way, I think this question is a non-question. It's strictly speaking not a precise question. But the way we understood it, the best way we should answer it is, I think, yes, the moon is there when nobody looks. And there are many ways in which this is the right answer, I think. Like, one of them is, certainly the moon will not be in a weird quantum state, but it will have decohered very quickly, like due to single photons that decohered in 10 to the minus 20 seconds to a state that's quasi-classical. So if we try to interference experiment with it, it would fail, for example. Right? It would also mean that different observers who look on the moon, or we look at some indirect records later on, and they will all be consistent with the moon having been there, and so on. So the answer would be yes. Even asking the question rests on the insistence of relying on this metaphysical picture that I think is just an approximation, and that quantum theory tells us is ultimately fundamentally not quite right. It's just yes to good approximation, our classical picture of the moon just sitting there does apply. That's what you could say. Would you agree? I guess you must agree.
Yeah, I agree, and I have to say I'm struggling myself, not so much to answer the question. My answer would go basically along the same lines as yours, but in really clarifying all the ingredients of the question and the resulting answer. So I would say something like, I'm improvising, so I haven't really thought very deeply, or I don't have a precise opinion. But the point is that I would say that to the extent in which I can make precise the question, so I can define what I mean by the moon, by the position of the moon, and so on, which implies within quantum mechanics a number of approximations. To that extent, the answer is clear. Yes, the moon is there, regardless of whether I look at it or not. Yeah. The problem is exactly that if my model of the world, including the moon, is quantum mechanics, a number of the ingredients in the question are not really there. I mean, they have to be found in some approximation, as you said. And so it's not that the moon is there only in some approximation. It's that my very notion of something being a given position is the result of some approximation. But anyway, I don't want to discuss. This discussion could go on for forever. And it would be interesting to have it, but also with a lot of other people. I want to close with just one question, which is mainly for myself. I don't know if the audience, the people listening would be so interested in that, but I work on quantum gravity. So, and I'm also very interested in foundations of quantum mechanics and foundations of physics in general. Sometimes I do okay, I don't want to say that I wake up at night because I tend to sleep well, but I do wonder myself if I'm distracting myself from my work on quantum gravity by asking or by studying or by looking at all these issues in the foundations of quantum mechanics. Would you say that? I mean, please reassure me, or at least give me some real reason to doubt. You see a relation between problems in quantum gravity, that is, the nature of space-time, or the things having to do with fundamental cosmology and so on, and issues in the foundations of quantum mechanics?
Yes, absolutely. So I must say that I'm answering this question as somebody who is not an expert on quantum gravity. I find it extremely fascinating and I want to learn more and more about it, but I know very little about it. But I think not so much that area of quantum foundations that talks about and discusses interpretations, perhaps more an area that we have not really touched upon, for example, the area that proves theorems about, for example, reconstructions of quantum theory. What kinds of probability click probabilities can you have under a certain set of simple postulates? Answer is the behavior as predicted by Hilbert space quantum theory, right? Now, in this view, as I said, quantum theory is just one theory among many others that could predict detector clicks and their correlations. And then this kind of view opens up some interesting, I think, methodological possibilities. So something that Časlav here in Vienna did, for example, was to say, well, what if we drop some part of the formalism? It's the part that tells you that the causal structure is always definite. Maybe the causal structure is also in a superposition in some sense. What kind of detector click probabilities could I see in such a situation? And I think this is a fruitful question to ask that comes from quantum foundations research. Another thing we're doing is we're saying, what if we drop the assumption that it's exactly the quantum formalism? It could be whatever probabilistic theory, but we want that thing to fit into the symmetries of space and time. We want to be able to rotate our devices. We want to have something like spin and angular momentum. Is it only quantum theory or some other cousins of quantum theory that could still work? And so in some sense, quantum theory could be perhaps modified in some regime or so. So I think this is one corner where something methodologically fruitful can come out of this.
Yeah, I don't know if you want to add something before I do make any comment. I mean, I like very much the fact that you mentioned two aspects of the story of this possible relation. One is that, there are suggestions within quantum foundations when you try to drop some particular ingredient that you take for granted in usual quantum mechanics for the sake of it, not necessarily motivated by quantum gravity. And you mentioned the possibility of causality being indefinite or in some superposition. And then, I listened to what you're talking about among your quantum foundations friends, and I jump in unexpected and uncalled for and say, oh, wait, this is exactly what we are wondering and what will come naturally in quantum gravity, that causality itself will be fluctuating or be in some superposition. So this is sort of the substantial aspect of the story. There are things that you are interested in quantum foundation that, maybe it's a coincidence, but they end up being very central and very natural issues for any quantum gravity approach. I mean, whatever strategy you decide to pursue for constructing quantum gravity. The other thing you also mentioned is also very important, the methodological aspect. And let me take it from the other side. I mean, working on quantum gravity, what basically everybody does, I mean, almost everyone, is we take the quantum mechanical formalism for granted in its mathematical ingredients. Mm-hmm. And we often don't realize that those mathematical ingredients have a justification as a coherent, logic, only assuming a number of things which are about space-time and causality and evolution and time and so on, that are exactly the ones that we cannot rely on in quantum gravity. So it's clear, it is clear from quantum gravity that a more general methodological approach would be very convenient, in which you say, okay, let's assume that some more general theory of probabilities, probabilistic reasoning about observables is there, and let's see if we can construct such theory about space-time. And then we have to ask our quantum foundations friends, and we say, okay, which probability theories are you considering, and how are they related to usual quantum mechanics and to usual classical mechanics, and so on. So, what did I want to say? Nothing. This is why I found it personally very natural to talk to people working on quantum foundations and thinking myself about quantum foundations a bit.
Right. I would certainly love to learn more from quantum gravity colleagues where we could be helpful, where you see steps where such a thinking could really combine with what you guys do.
There is this party that we were mentioning earlier that we are going to meet, so maybe we can do that over a glass of wine.
Yes. Yes.
Okay, very good. So I've taken too much of your time already, but I really enjoyed it. So I hope that
Thank you.
Yeah, I hope that whoever listened is also enjoyed